Right. So we have 7 different solutions with increasing amounts of sucrose in it. What does this mean? W/W%. You may have seen that in like the hospital setting or some other settings. W divided by W%. What do you think the W stands for?
Isn't it the sucrose over a solution of water?
But what's the W stand for?
Is it weight?
It's the weight. That's right. Excellent. That is a weight by weight percentage. So basically what we're saying that it's by weight, not by volume. Okay, so of the total mass of solution number 2, the total mass, what will the total mass of solution number 2 be?
$55.5.
Right. And the sucrose is 5.5 grams, which is 10% of the 55.5. So it's based on a weight percentage. Sometimes we're going to have weight by volume. Other times we're going to have volume by volume. So it's important that you know what the percentage means, because if we have 2 liquids, generally those will be volume to volume percent. So pay attention to what the percentages actually are. When we're dealing with solids, usually it'll be a weight to weight or weight to volume. Here we're doing we're just looking at just the masses and the percent mass of sucrose. So we're going to make each one of these. The last 3 are a little bit tricky because you may have to warm the water in order to get the sucrose to dissolve in it. That's one of the reasons why it was suggested you do not use cold water or cold water out of the tap. You want to use filtered water or bottled water that's been sitting at room temperature for at least a few hours. So because if it's cold, it'll be even worse at trying to dissolve. So you may have to pop these things in the microwave for like 10 seconds at a time. Not too long though, because I think these cups will melt. So you just heat them up just a little bit at a time till you get them all dissolved in solution. Okay. All right. So here's where we'll just determine the densities of the different solids. You just put in the mass, the height, the diameter, calculate the volume, calculate the density. So like I said, we're going to be using this later because you're going to figure out what the densities are of the different solutions. And then you're going to have to make a prediction as to whether or not these things are going to float in that solution or sink in that solution. So we'll have to figure whether the densities of the solids are less or greater than the densities of the liquids. So that's like the last thing you'll do. All right, so this is basically the instructions. It's fairly straightforward, and I'll go through it with you. What we're going to be doing is just taking 50 grams of water. This is the first determining the density of the different solutions. The very first solution we're going to be using is just water all by itself. So what we're going to do is basically calculate the mass of 5 mils of water, 10 mils of water, 15, 20, and 25. And then we're going to plot the masses and the volumes using our computer, whatever program you want to do, and we'll figure out what the mass, what the density of water is. And you should get pretty close to 1 gram per cubic centimeter, or 1 gram per mil, which is the same. Remember, a cubic centimeter is the same as a milliliter. These two are precisely the same volume. So once we've done that, we'll take our next solution, which is the 5% sucrose, and we'll do the same thing. And then the 10% sucrose, and do the same thing. And you don't have to do the plotting tonight. Basically, you want to do all the work tonight, and then you work on all the calculations later, okay? So here's the data table to fill out. And so you're going to measure the mass of the graduated cylinder. I'll show you what hopefully everyone knows what graduated cylinder is by looking around in your box. So you count, let's say the graduated cylinder is 75 grams. And the mass of the cylinder plus 5 mils of water is 80 grams. So then the mass of the solution is 5. And so the mass of the cylinder should stay the same, basically all the way through here. And we just subtract it so that we know what the mass of the liquid is inside. And so this is what you're going to be plotting. Mass of the solution and the volume of the solution. So which one, when we're plotting that, which one is going to go on the x-axis and which one is going to go on the y-axis when I'm plotting mass and volume? And I want to get density.
Volume would be X and mass would be Y.
Okay, so we put volume here and mass here. So this would be mils and this would be grams. So then when I get my plot, what's the slope of this line going to be? When I get my y equals mx plus b.
Linear?
It'll be linear, but what will the slope be? What will the
Positive?
units of the slope be?
Oh, the units of the slope. It'd be in what is it? Grams?
Nope,
No.
Grams over ml.
that's right. That's right.
Oh.
Because you've got grams is the y, and volume is the x. So right, so that's what you want to plot if you want to get mass over volume, and that is indeed what you want to get because we want to get density. So that's what you'll plot. So volume on the x-axis in milliliters, and mass on the y-axis in grams. And so the slope of that line should be grams per mil, and that is units for density. And so basically what you're going to do is put them all in the same graph. So what you should see when you plot them all there is you should see another line that looks like this, and then another line that looks like this, and then another line that looks like that, and then another line that looks like this. Your density should be increasing as you put more and more, as you dissolve more and more solid in the solution. And so your density should be increasing. So the slope of this line, so if this is the 0, this will be the 5%, this will be the 10%, 15%, 20%, or whatever the amount of sucrose is. Probably it's more than that, I think. But the more sucrose you add, the higher the slope of that line should be. And remember, the slope, the m and the mx plus b, is equal to your density in grams over mils. So make sure you plot grams and milliliters, not any other don't plot kilograms or liters or anything like that. You'll get completely different results. So here's the results you'll get. So these are once you've plotted all those lines, like I said, you'll get a line with y equals mx plus b. And it actually asks you, remember like last week, we did the y-intercept equals 0 trick. That's why we did that, because we want to have the y-intercept be 0 for these experiments. Because if the mass is 0, then the volume is also 0. Right, so that should be our first point when we're plotting. We're not going to actually plot it on the graph ourselves, but we will include it by forcing the y-intercept to be 0. So instead of y equals mx plus b, we're just going to get an equation y equals mx. And so there is the slope, and then you put it right there, and the next one over. So you should get around 1, and then it increases as you go down. Okay. Any questions about how to do that part of the lab? About how to handle your data? No, everyone's pretty clear. Okay. And then the next one is, once we've figured out what the density of the aluminum cylinder, and the acrylic, and the polyethylene, we just compare it to our calculated densities for the different sucrose solutions. And so if you're going to stay up late doing this tonight, you can actually do the experiment, or you can do it tomorrow. Just put so with your solutions of sucrose, just put some clear plastic wrap over the top of them, and then do it in the morning once you've done all your calculations. Then fill in your predictions, either S for sink or F for float, and then just see whether the observations agree with you. Okay. And then the last one, and this is something you can do tomorrow or later in the week, is once you have a beverage, and remember I sort of suggested you want something clear, like milk's not going to work because there's way too much other stuff in it. We want something that basically the density is going to come from sucrose. So you're going to want something like apple juice, or orange OJ that doesn't have any pulp in it, or iced tea is a good one. Make sure it has sugar in it, of course, or some kind of soda that you've allowed to go flat. So then once you have that, you're going to basically do exactly the same experiment. You're going to figure out what the mass of 5 mils, 10 mils, 15, 20, 25, and then plot it and get the density. So then you're going to get the density of your beverage. So, but that doesn't tell you what the percentage of sucrose is. You just have the density. So how are you going to do that? Well, you do that by making yet another plot. But first, does anyone see what's wrong with this table? This is right from your directions, and there's a big mistake in it. Anybody see it? It's a problem with units.
Is it the beverage?
What about the beverage?
The unit should be Should it be milliliters?
Nope.
No. Okay.
Well, the problem is in the volume column.
Oh, volume should be mil. Wait.
Centimeters
mind.
cubed.
Go ahead.
Should it be in centimeters cubed?
Nope, that's no. Centimeters cubed and milliliters are exactly the same thing.
Oh,
They
It's-
include percentages.
There you go. Yeah. There's no such thing as 5% mils. There's 5 mils, but there's no such thing as 5% mils. I think the problem was because they were trying to get to yet the next step, which is how are you going to determine the percent sucrose from the density? So if we have the density of a beverage, how are we going to use that to determine the percent sucrose? How do we do that? Just think about the information you're going to have at hand.
wouldn't you just use the mass of the beverage over whatever the volume is?
That just gives you the density. That doesn't give you the percent sucrose.
Oh,
So using this data will give us the density of the beverage that we will have. We won't have the percent sucrose though. How are we going to convert this to this? I'll give you a hint. We need to make yet another graph. So what are we going to plot in order to determine the relationship between density in grams per mil and percent sucrose? How are we going to figure out what that relationship is? So just think about what you've done in the experiment to this point. What solutions have you made? What solutions are you going to make?
sucrose percentages over density.
Well, you're not going to make density solutions. You're going to make percent sucrose solutions, right?
Right.
And then, so what are you going to do with them? Once you've made your
Wait,
percent
wouldn't you-
sucrose solutions, what are you going to do with them?
Wouldn't you compare it to like the when it was? Never mind. I'm thinking of something totally weird and different. Yeah.
No.
I was just thinking that
You are going to
Oh.
compare it to something. What are you going to
like the
compare?
water, like of it just being water, I guess. But then that wouldn't work because you got it as a beverage already, so like it's already mixed. So I'm like,
Basically,
to the
you wanna-
density of water, right?
Well, you want to see if the density is greater than water.
Yeah.
That tells you whether or not there's sucrose in it. But how are we going to determine the actual percent? I mean, we want to be able to calculate, that it's 7% or 13% or 17%. How are we going to do that? So you're going to have 6, or is it 7? 6 or 7 different solutions with different amounts of sucrose. And you will have calculated the densities of each one of them. Now, what are you going to do with that information? so that we could use. So if I have a density of an unknown solution, I can figure out what the percent sucrose is. How am I going to use these two pieces of information in order to figure that out? Using a plot. Just think, which one of these is the independent variable, and which one of them is the dependent variable?
Sucrose is the independent, right? And then
That's
density
right.
Would be the dependent.
That's right. The sucrose is the independent variable because we have decided what percent sucrose solutions we're going to make. And then because we've made those specific percent sucrose solutions, that affects the density, which is the dependent variable. So where are we going to plot percent sucrose?
On the X.
On the X, that's right. So we're going to take our X values will be our percent sucrose. We're going to put those on X. The Y will be the density because it's the percent sucrose that determines what the density is in grams per mil. And then we're going to plot them and get a line. And from that line, we will now have a formula that tells us what the relationship is between Y, which is density, and X, which is percent sucrose. So when I have figured out what the density is for my beverage, let's say it's here, I just go over here, go down, and now I know what percent sucrose it is, okay? Does that make sense? Basically, we're taking the data that you're going to be collecting tonight and then using it in a subsequent step to actually help you calculate something. Go
How
ahead.
would you find grams per milliliter for a beverage?
That's the density. So we're going to measure the
Yeah.
volume.
Mhm.
So you're going to measure the volume. You're going to measure 5 mils, 10, 15, 20, 25 mils. And then you're going to measure the mass, whatever the masses are. And we're going to plot those, and the slope of that line will be grams over mils, which is density. So we're going to have the density of all our different sucrose solutions. That's the first part of the experiment. And then the last part is that you will then have exactly the same plot for your beverage, whichever one you picked. And that will be grams over volume, which is the slope of that line will be density as well. So any questions about how we're going to get started?
I'm so confused on like how you would
Okay.
find the mass of a beverage.
By weighing it.
Oh my gosh, I overthought it. Jeez Louise. My bad. I keep on doing that. Oh my
Yeah.
gosh.
Yep, by good old weighing it. Okay. All right, so I'm going to move my computer over to my workspace. Actually, but before we do that, why don't we just do the first part of the experiment? That one we don't even need to put our goggles on or anything. We're just going to measure the 3 different cylinders. So here's our polyethylene, acrylic, and aluminum. So you should have a ruler in your kit. Hopefully you've found it by now, or you have another ruler. So remember, all we need to do is determine the height and then determine the radius. Everyone remember what the radius is?
Diameter divided by 2.
There you go, exactly. And that'll give us the volume. So So it's pi r squared h, right? I believe. All right, so the height. So some of these might be a little bit tricky because I think especially with the, you have to be careful, especially with the plastic and the acrylic, they can be chipped. So it might be a little hard to get a precise measurement. And remember, we do not use inches ever. We use centimeters. The other thing to remember when you're doing this measurement is you always estimate the last significant digit, right? So if I'm going to measure mine right here. And 1, 2. So I've got 12 millimeters and then a little bit more. 11, 12, maybe 12 and a half. So mine doesn't fall precisely on 12 millimeters. I just know it's more than 12 millimeters, but it's less than 13. So I need to estimate that last digit. So I'm going to estimate it as, let's see. Which now it is right on 12. Yeah, 12.3, I'm going to say. So even if you measure this in millimeters, are we going to use millimeters to calculate the volume? See or no? Oh,
No.
Should we use millimeters to calculate the volume?
No.
No, that's right. So convert everything to centimeters before calculating your volume.
I thought all of these cylinders had the same height.
Yeah,
They're
same.
not, I mean, they're not going to be exactly the same. They're going to be really close. Everyone should be pretty close to each other, but they're not going to be exactly the same. Like down to 1/10 of a millimeter.
I got eyesight problems. This is
Because that's
gonna be
what you
tough.
should have. You should have 3 significant digits in this measurement. The first 2 come from the ruler, and the last one comes from you. So you should have 3 significant digits here. You're going to have to estimate what that last digit is. So if you're measuring the diameter or the height, they're all going to be around 12 millimeters, it looks like. But if you have exactly 12, what should you report as the height?
4.0.
That's right. Man, Vera, you are on top of this. Yeah, because you have to have 3 significant digits from this measurement. So if it's exactly 12, as far as you can see, then use the 0.0. Oh, here it is. Yeah, I'm already seeing some little variation in between each one.
Professor, I have a question.
Mhm.
How did you get 12? Like, I'm really confused because first you said centimeters and then you said
Oh,
millimeters.
I'm using the, so in between. So that is one centimeter, right? And then the units in between are millimeters. So I was just measuring it in millimeters.
Oh, okay.
And then I'll just convert it back to centimeters when I do the calculation. Yeah.
Do I have to do it on a different paper now because of the errors I made?
Or you can just print it out again. I mean, that's, yeah, just you can write whatever you want on that, and then you can,
Okay.
you could type your
Because I know
report.
you didn't want it messy or anything.
Yeah, well, then you could just do it over. Yeah, I mean, I just write on, like, when I'm doing my calculations, I just write it on anything. Like you should have a book that you put all your experiments in. You should have a book of some kind. And then you do all your calculations and everything in there. And then you put it in the final report once you've finished everything. That should be neat. So yeah, don't take your notes on the report itself.
Oh, okay.
That's for when you're done. Yeah, it's tricky to measure the diameter to be exactly halfway. Yeah. Okay. So then we just use pi r squared h to figure out what the volume of each one of them is. And then we're going to use our balance to get the masses, okay? Oop. What is that noise?
Oh, sorry. My dad's making like cutting up meat and stuff that he bought.
Oh, I was wondering what that was. Sounded like somebody was burping a collie or something. I couldn't tell.
And did you want us to round to the most three significant digits?
Well, you should have 3 significant digits in your height. You'll probably only have 2
Oh, I mean for
significant
the
digits in, well, no, you should have 3 significant digits in your radius as well. So then
no.
your final volume should have 3 also.
Okay.
I got 2 sig figs for my height. Is that all right?
No, you should have 3.
3. I can't really like see if it's like, do I just add a 0 if I think it's exact? Even that's probably not. Or do I just like add
So
like
if
some
it's right on
hypothetical
the
number?
0, you put 0.0. If you
Mhm.
think it's a tiny bit above it, you put like 0.1 or 0.2. If you think it's a tiny bit below it, then you put like 0.9 or 0.8. Yeah, it's a judgment call. That last digit is a judgment call on your part.
Okay. So then I'll just put like 0 then.
Yeah.
And that'll be 3 sig figures in. Okay,
Yep.
sick.
Mhm.
Thank you.
No worries, no problem. So is everyone getting around 1.4 cubic centimeters approximately?
For the volume or for the density?
For the volume?
I got 1,400 and something.
It's because you use millimeters, not centimeters.
No, I use centimeters.
No, you didn't. Oh,
Isn't this part of the ruler centimeters?
yes. And then each smaller marking in between them is millimeters.
Oh. So if I measured something on the scale and it said, 12.5,
Then it's 12.5. That is 1.25 centimeters.
so
So these smaller, like 1, 2, and 3, those are centimeters. In between there's 10 gradations in between each one. Those are millimeters. And then you want to estimate inside the small gradations. So your measurement, if you went 10, 20, 30, you're measuring in millimeters. Our calculations are always going to be in centimeters
oh,
for density. Okay. All right, I'm going to move now. So I'll be back in a sec. All right, so I've calculated my volumes. Hopefully you've calculated your volumes at this point. So I'm not sure which balance you have. Does it look like this or is it a white one? Okay. All right, yes, this is the one we got last year. It still works, so I figured I would use it. So a couple things. Like I said, you want it to be flat. And then when you're not touching it, the mass, now that I'm blowing on it, it does. You want it to be somewhere where the mass isn't going to be changing. Mine's fluctuating a tiny, tiny bit. So the power, on one side you have M button, on the other side you have the power and T. T stands for tare. So we hit that and we should go to 0. Other thing you want to look for is with these balances, a lot of the times they will measure things in grains and also in carats. Like if you want to see, if your significant other gave you a rock as big as they claimed it was. So make sure that there's a little G. I don't know if you can see that. There should be a G there. Sometimes you will see a GR, that means grains, or CT, that stands for carats. So just keep hitting the left button until you get the right units. You want G for grams, okay? So then you just hit tare, go to 0. and then just pop it on and read it. And you should get 3 significant digits from your mass. And you wait for it to stop moving. As long as I'm blathering, it's moving a little bit. So my aluminum cylinder is 4.33 grams. So I'll go write that down. And then when you take it off, if it goes back to 0, you don't have to tare it. But it's probably a good idea to tare it anyway. So it's always at 0. So it's a good habit to get into. So my acrylic, much lighter. 1.88. And finally, the polyethylene. Tare. 1.53 grams. Okay. So it's just a quick calculation to figure out what the densities are. And I believe in the instructions, they give you an estimate of what your density should be, don't they? I think the polyethylene should be around 1. The acrylic should be a little bit more than that, and the aluminum should be around 2.7 grams per mil. Ooh, my aluminum is high. Yeah, so I got 3.14 grams per centimeter for aluminum. So my aluminum is off. You should get around 2.7. My acrylic is 1.31 grams per centimeter. The polyethylene looks to be around 1. Yeah, 1.09. So we have to assume that the aluminum is probably going to sink in every situation, because I don't think we're going to be making a solution denser than 3 grams per mil. Seems unlikely. All right, so that part is pretty straightforward. Next, we put on our goggles. Yeah, because we don't look nerdy enough. Nice and nerdy. Even if you're wearing glasses, it's a good idea to have them on, because these have sides on them that your glasses do not. So even though it's a pain, you may think you look like a dweeb. You do look like a dweeb, by the way. We all look like dweebs, so it's fine. So this is your 50 mil graduated cylinder. You can tell it's a 50 mil graduated cylinder because it says 50 on it. There's graduations and it's a cylinder. So there you go. So when you are measuring volumes with this, it is really important to get down to the level of where the graduations are. Because if you're looking from the top, you really can't tell what the volume is. And what's the other thing we need to look for when we're measuring the volume of water? Anyone remember what happens with water when you pour it into something like this? Is it flat?
There's a bend in it.
Yeah, there's a little bend in it. Anyone remember what that's called?
A meniscus.
Meniscus, bingo. Yeah, so it's going to be a little bit curved, because water, as we will find out later, is one of the most wondrous things in the world. I'm constantly yakking about water. Water likes to stick to itself. It's it's due to that we have capillary action. It's why redwood trees can grow to be, 1,500 feet tall. If water didn't stick to itself in a column, they couldn't do that. So water actually will stick to itself and then start moving up the sides of the container. And so what we want to look at is the bottom of that curve, not the top, but the bottom. And the way we're going to transfer water is with one of these. Anyone know what one of these is called?
A pipette.
Pipette.
Pipette. Man, you guys are all over it. So here I've just got my filtered room temperature water. Here I've got I'm going to measure the mass of my cylinder. .38. Everyone's is going to be slightly different than that. But I want to make sure 29.38 for the cylinder. Because what you don't want to do is to be pouring water into this thing on top of the balance. Because if you spill water on it, it's toast. So we take this, and to measure our 5 mils, we just we squeeze the bulb and transfer in here. Meanwhile, we're holding it up so we can see. Another thing we want to avoid is having the water stick to the sides. So like I said, water likes to stick to itself. So sometimes it will stick to itself on the side of the container rather than flowing down. So we want to make sure it doesn't do that. What makes it a little tricky to read this with glasses on. Okay, that's almost fine. Another thing you want to do, you might want to put something dark behind this. If you like a dark piece of paper or something like this, it's really hard to read the numbers because it's a clear container, it's got clear numbers. If you put something dark behind it, notice how much easier it is to read. So that's pretty much impossible to read. And now that's a lot easier. I don't know if you can see how much easier it is, but take my word for it, it's easier. All right, that's pretty close. Now I'll just measure. 34.58. So then you just keep going. So you put 5 mils in here, measure the mass. Put 10 mils in here, measure the mass. 15, measure the mass. Up to 25. And then we can start making your solutions.
Professor, I have a question.
Okay.
So are we not putting any water in our cups yet, or are we doing it, putting water in our cups yet?
That's the next step.
Okay,
Yeah, first I was just, you can
Thank
do it in you can do it pretty much in any order you like. So I was just going to measure the mass of just the water first, and then make my solutions. But if you want to start making your solutions, that's fine. So to make the solutions, we have the instructions here.
Professor?
Yeah.
Since water's like 1 gram per milliliter,
Mm-hmm.
can't we just add 5 or like the number of milliliters, right, to the mass of the cylinder, and that'd be what you get?
No, because you're doing an experiment. So we need to, no, that's
Yeah,
not,
yeah, I know.
no, the
I
thing
get
is,
it.
we need to determine what the errors are.
Oh, okay. Yeah, yeah.
So you won't be able to do that with your solutions. So you want to have the exact same error in the measurement of water that you do for everything else. That way, everything's kosher. You know what I mean?
Mm-hmm.
So yeah,
Okay.
yeah. It's not because we're torturing you or anything. It's because we have to figure out what our accuracy is, and basically we're using the water as a standard to figure out how accurate our method is. Because without knowing how accurate your method is, it's kind of pointless doing the experiment.
Yeah, that's
Right.
Yeah.
So if you get a radically different answer than 1 for the water, well, then you know the rest of them are kind of suspect as well. But if you get something close to 1, like 1.1 or 0.95 or something, then you're doing a fairly decent job. All right, so for making the solutions, where are my? So I'm just going to make the 10%, right? So we want 50 grams of water for each one. So we measure our 50 grams of water. So that should be around 50 mils. But we want to weigh it to make sure. So here's where we use our tearing function. So I'm going to put my cup that I've labeled 10%. I put it on the balance and I see my cup is 10.17 grams. Then I hit the tare and now it says 0. So anything additional I add to the cup, the mass of the cup will not be considered, just the mass of the water. Okay, so I've got my 50 mils of water and I'm going to pour it in. And it should be, oh, that's a little bit more than 50. So I'll take the water out with my pipette. And I just add it in drop by drop until I have 50.00. There we go. So 50.03, that's pretty close. So I've got 50 mils of water in here. Now, when you're measuring the mass of a solid, you're going to use one of these. Anyone know what this is called? That's kind of a silly name.
A weighing boat?
Oh,
A weigh boat, that's right, a weighing boat. So we do the same thing with the weigh boat. We put that on top of our balance and we hit tare for that as well, till it goes to 3 zeros. So then to add the sugar, and you can see I brought enough for the whole class. You can just use a spoon and just add the sugar until you get to 5. So here, it's kind of good idea to be gentle. Don't just dump it in all at once. Just sort of tap the spoon lightly. Because it's really hard to get the sugar out again if you go over. It's best just to tap lightly, do it a little at a time.
Professor,
Yep,
I have a question. Where'd you get the sugar from? Is it from Lab Kit also?
nope,
Oh,
this,
my
no,
sugar.
this is, should be in your kitchen.
Okay, thank you.
And I have a 11-year-old who loves to bake, so we've got lots of, my God, we have a lot of sugar. He's not helping daddy's waistline at all, I can tell you that. All right, so now that I have my 5 grams of sugar, nice thing about these weigh boats is you can bend them. And when you bend them, you can see you make a nice scoop in order to dump it out. And then just dump it. You can even tap it a little bit, make sure you get all of it out.
Wait, how many milliliters of water is in that cup again? Sorry.
50 grams of water.
Okay.
So what I did was I measured 50 mils and put it in the cup and then see how close to 50 it was. If it was more than 50, I removed some with the pipette. And if it was less than 50, I added some with the pipette until I had 50.00 grams in the cup. So now I've got 50. Oh, was I supposed to put 5.5? Oops. So I need to put another half a gram of sugar in there. I made a mistake. So I need another half gram. I have to be super careful with this one. There we go. And then you just use a spoon to stir it. So I've got like 1 spoon for measuring, 1 spoon for stirring. And so what you can do, you can either make all the solutions at once and then do your weighing. That's, or you can do them one at a time. It probably might be best, especially if you want to finish the experiment tomorrow, to make all the solutions tonight, and then you could do the calculations tomorrow.
Professor, I have a question.
Yeah.
So,
Mhm.
sorry, I'm a little behind. So after we put 50 milliliters of water,
No, 50 grams of water.
I mean 50 grams, sorry.
Yeah.
What do we do after that?
Then we add our sugar.
Okay, we add 5.5 grams of sugar?
It's in, you should know because it's in the procedure. And you've read it, of course. And you don't have your goggles on. You're going to get sugar in your eye and you're going to be blind, and it's going to be my fault, and I'll just never forgive myself. The question is, how do we know when this is all in solution? How do we know when all the sucrose is dissolved? I'm just going to keep stirring it. I mean, when can I stop stirring? When is it done?
When it's dissolved.
How do you know?
Can't see it anymore.
Can't see what?
The sugar anymore.
There you go. Yeah, again, it would help to look at it against a dark background. I've got a little sort of diaper on the table in case I spill something, and it's white, so I can't really see white crystals. But if you have something dark, it's real easy to see. I don't see any little floaties or anything, so I think I'm good to go. So that would be my 10%. Then go ahead and do, was it 10, 20, 30, 40, 50, 60, I think, percent. Like I said, the 50 and the 60% are going to be tricky. You may have to heat them. But then if you do heat them, make sure you let them go back to room temperature before you measure. Why is that important? Why is it important for the solutions to be at room temperature when you measure the mass?
Doesn't heat affect the temperature? I mean, you know, the heat of the solution, wouldn't that make the mass?
It doesn't affect the mass. It
Oh, it's
affects
like the-
something else.
The volume?
Yes. It affects the density. So the hotter something is, the more the particles expand away from each other. And so the volume will be slightly higher and your density will be slightly lower. So the density of water is 1 at 25 degrees, which is like the 25 degrees C, which is sort of thought of as, standard temperature for liquids and solids. At lower temperatures, the density is higher, and at higher temperatures, the density is lower.
Oh,
So remember to measure the mass of the water, not the volume. So 50 mils of water is a good approximation of 50 grams, but it isn't precise. The only way to get a precise amount of 50 grams is to use the balance.
Hi, Professor. So I'm also
Yes.
actually up behind because I'm just really slow, but like just
No
to
problem.
just to clarify, because I was still doing the first part when
Mhm.
you were still continuing. Okay, so
Okay,
I have my 10% water, right? So
okay.
10% water.
Not 10% water, 10%
I mean,
what?
it's the cup. So
10%, what's it 10% of though?
oh no, this is I don't know, I just labeled the cup 10%. This is the one with the first thing we're doing. when we're
Right, but
adding
what is the solution? Is 10% of what?
of the sucre,
It's 10% sucrose, right? There you
Yeah.
go.
okay. So I just put this on the scale and then tare it, correct?
Mhm. So
So-
it reads 0, and now add 50 grams of water.
Okay.
So the way you do that, is you measure 50 mils of water, approximately, in your cylinder. You add that to the cup. That should be approximately 50 grams. And then you make it precisely 50 grams by either adding or taking away water with your trusty pipette here. So then once you've got 50.0 grams, then take the cup off and then use the weigh boat here to measure 5.5 grams of sucrose.
And so just do the same thing, like put that on here, tare it, then put 5.5 sugar.
Yeah, except we don't measure a solid in here because there's no way to remove the solid from this if we add too much, right?
Yeah,
So
so
what we're going to do is use the weigh boat here. This is what we use for measuring solids. So we put this on our balance.
Mhm.
See it here. Then we hit tare so that it reads 000. And now I put 5.5 grams of sucrose in the weigh boat. And then once I've got my 5.5 grams, then I transfer it to the liquid and then stir it until it's dissolved.
okay. Thank
Okay?
you.
Yeah, because if we added the solid directly to the liquid, if we went over, there's really no way of removing solid from a liquid. Once it's dissolved, it's in there. So can't really do that.
For my measurements, you know how I got it in millimeters and then I had to convert that to centimeters.
Right.
Can I just move the decimal one place to the left?
That does it. That's dividing by 10, right?
Yeah.
Mm-hmm.
Okay.
Yep, that's how you divide by 10.
Okay. So the volume should be less than 2 for the 3 solids cylinders.
Yeah, I got around 1.4 mils for each one of them, or 1.4 cubic centimeters for each one of them,
Okay.
approximately. I mean, it's really hard to get a precise measurement with those rulers.
Yeah.
And if you're off by just a little, once you start squaring things, then, it goes to hell pretty quickly. So if you're even close, like I got 3.1 grams per cubic centimeter for aluminum, and the real amount is 2.7. So that's not bad. I mean, that's
Okay.
like a 10% error.
Because I wasn't sure if
take that.
during this experiment you wanted us to all have the same exact numbers.
Same exact numbers of what?
Like for example, the volume of the water, and then calculating the mass.
Well, I mean, those should be close to each other. I mean,
Okay.
some people won't have exactly 5. They'll have 5.6 grams. Other people have 5.49 grams. I mean, you're not going to have exactly the same masses.
Okay.
I mean, really, it's all going to come out in the slopes of the lines. That's the most important thing, because there's so many steps to this experiment that, a little small mistake here, a little small mistake there really won't make a huge difference unless you keep making it over and over and over again. That's the
Okay.
difference. That's the difference between a systemic error where you're doing something wrong over and over and over and over, like not knowing how to use the balance properly, or forgetting to tear it or whatever, and doing that over and over, and just random errors. Random errors sometimes, if you're lucky, will just sort of balance each other out. One point will be a little below the line, the next one will be a little above the line, and you'll draw a perfect line in between them. So I don't worry too much about little small random errors. They tend to take care of themselves. It's the systematic ones you really got to look out for. All right, I'm going to start measuring the masses of my solutions. So then I can work on plotting them to show you how that's going to work, okay? So I'm going to do water, 0% sucrose, and 10%. Okay. Oh yeah, you should have something to dump things in. Once you've measured your solution, you just want to dump it in something. So you should have a big, I think there should be a fairly big beaker that came with the kit, like a 500 ml plastic beaker. That's a good one to use, or if you just have just a big bowl or something, because this stuff, I mean, it's just sugar water, so you can pour it down the sink. But for future reference, you're going to want something around you can dump waste into to keep it from accumulating everywhere. Okay. And when you're measuring the mass of your solutions, you don't have to dump out 5 and then add 10 and then dump out 10 and add 15. Just keep adding to it, right? That way you save yourself a lot of trouble. I don't even know if you'd have enough solution available to do that. So I just keep adding 5 mils and checking the mass. Okay.
For the 50 grams of water, you just use the granulated cylinder and then you just added the water inside to measure it, correct?
I'm sorry, what was the question?
So if I'm trying to get to the sucrose solutions,
Mhm.
and you know, the consistent number is 50 grams of water. So
50
to get to
grams.
50 grams, you just use the granulated cylinder and then you just use the weight to measure 50 grams.
Graduated cylinder doesn't measure mass, it measures volume. So put 50 mils in the graduated cylinder and then take your empty cup. So have an empty cup, pour the 50 mils of water in there and then weigh it. So weigh the cup, tear it back to 0, add the 50 mils of water from the graduated cylinder and see how close to 50 it is.
Okay.
If it's less, add a little bit more. If it's a little bit over 50, take it away with the pipette. But remember, this measures volume, not mass.
Okay.
Yeah. Okay.
Professor,
Yes.
I may or may not have spilled, like, well, I was stirring it a little bit. I was stirring it a bit too enthusiastically, and
Dylan, you do something enthusiastically, I have trouble believing that.
nice.
So, do you spill? Yeah, I mean, that goes down as a source of error. Just make a note.
Okie dokie.
Yeah, don't worry about it. These things happen. Yeah, I mean, if it all dissolved before then, no harm, no foul. But if it hadn't, then there's going to be a little bit of
Yeah, it has.
Oh, then it shouldn't be a problem. Unless you've spilled all of it, then that is a problem.
No. It's like 5 drops.
If so, I put some water into one of the cups,
Mhm.
and when I tried to measure it with the weight, it didn't give me a number. It just said owed.
Oh, over. So
Yeah.
make sure you're on grams. If you're on carats or something, then that'd be way over.
No, I am on grams.
Well, that shouldn't. I think these go up to 100 grams, so that should be fine. So
'Cause,
how much? So yeah, so this weighs like around 30 grams, and then 50
Oh.
grams of water should be around 80. So you shouldn't be over 100.
Okay, because yeah, it just says owed. Wait. It just says old on the machine.
All right, yeah, just
That
turn
means
it,
it's too heavy. That means it's too heavy.
yeah, turn it off and on again. Yeah, these cups are even less, so you gotta have more than 50 grams in there.
Mm.
Yeah, because the cups weigh around 10 grams and the cylinder weighs 30. So either of those you should be able to
Oh,
put 50 grams.
That's
in there.
why I use a different scale, and the grams is 115.
That's way too many. 100.
Yeah.
So what are you measuring? What weighs 115 grams?
It was the water with the plastic cup.
Yeah, it's way too much. That can't be 50 mils of water. So put the cup in, zero it, tear it, and then add the 50 mils of water.
Professor,
Mm-hmm.
I have a question. So for 10% one,
Mm-hmm.
I did all the 50 ml water and then 5.5 gram. And after that, what I do?
Stir it till it's all dissolved.
Yeah, it's dissolved, and then what's next?
Well, you can either measure the, well, have you read the instructions?
Yeah, but I don't get
You
it.
can either make the next one, the 20%, or you can do what I'm doing. See, I've got my 10%. I'm measuring out 5 mils, and then I'm going to weigh it. So either one.
Does it have to be exactly 50.00 grams?
You want it to be as close to 50.0 as you can.
Okay.
Yeah, obviously you can't. I mean, I didn't get 50.00. I got like 50.03 or something. It's like, that's close enough. Yeah, we're not trying to split the atom here. So, don't worry. We're not going to worry about 4 degrees of precision.
Okay, yeah, because I got 50.04 for the 70% for one of the cups.
Okay, perfect.
For data table 2, right? It says on the left side, percentage of sucrose in solution, so 0%, 10, 20, and so on. Right? So would I have to put in that solution into the graduated cylinder?
That's the point.
Ah.
Yeah, so you put in 5, measure it, measure the mass, then put in another 5, and then measure the mass, another 5, measure the mass, another 5, measure the mass. So I'm doing that with my 10% right now.
And then after you're done with that, then you just pour it all back into the cup? Or do you have to make a new batch?
No, don't make a new batch. No, you can just dump it.
Okay, cool. Phew.
Yeah, just dump it. You just need enough to see whether the cylinders are going to float or sink in it.
And like, if I'm gonna do all the calculations tomorrow for this, right? Where would I put the solutions? Because I kind of
Well,
like.
just put some saran wrap or some plastic
Okay.
wrap over the top.
Okay. Yeah,
Just
that's what I
leave
was
it at
thinking.
room temperature overnight.
Okay.
Yeah,
Thank you.
no problem. Or, I mean, yeah, that'd be the thing to do. If you just want to make the solutions tonight and then do the measurements tomorrow, that's fine. I was just going to show you how to do the plotting. So
Brown
it's gonna-
sugar works too, right? Because does brown sugar work?
sorry, I can't hear you.
Does brown sugar work too? It does, right?
No.
No,
No,
just
brown sugar has molasses in it. And so it's not pure sucrose. So that's going to throw off your results a little bit.
Aw, shucks.
You've been using brown sugar?
I mean, I don't know. It just says organic sugar and it looks brown.
Yeah, well, yeah, make a note of that too.
Oh, yeah.
Yeah, there's a difference between organic sugar and like really dark, like Demerara sugar has a ton of molasses in it. And so how you prepare that into like regular sugar, you just spin the hell out of it in a centrifuge, and that brings all the delicious molasses out and leaves you with sugar. Yeah, if I mean, if brown sugar is the only stuff you have, then that's what you got. But if you got both, then I would definitely use the white sugar.
Yeah, because right now I just been using the sugar packets, like what you put in coffee at the store. And so
Oh,
like I ran
wow, you're gonna go through a ton of those.
I know. That's why
I hope you
wasn't
have a few hundred of them.
No, I actually have no more. That's why I was asking if I can use the brown sugar next, because other than that, I
No,
haven't-
no, 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 no. If you're using white sugar to start, you gotta use it all the way through. You can't change midway.
So should I just stop the experiment, just continue tomorrow and buy
Yep.
sugar? Yep.
Well, I mean, have you finished the 10%?
I did.
Okay, well then, yeah, I would do the calculations for your 10% then.
Okay.
So measure the mass of 5 mils of it, 10, 15, 20, and 25. Same with the water. You should do that for the water as well.
Thank you.
No problem.
When you're trying to tar the scale,
Mm-hmm.
do you leave so like I'm trying to tar all of the plastic cups. So when the cup is on the scale, do I press tar?
Then you hit tear. Yeah,
Okay.
yeah. Because basically what it does is just subtracts the mass of the cup is all it does.
Okay.
But yeah, you don't do them all at once. I mean, you do them when you're using them. Like once you've tared that, then you have to add something to the cup.
And when you tear it, should it say 0 or because it still says the
should.
amount of how much it weighs?
It should say 0 once you've tared it properly. So it's the button on the right. It's the same as the power buttons.
Maybe mine isn't working because every time I press tear, it still leaves the same weight, or it just gives me all of the previous measurements.
The previous measurements.
Yeah,
Are you
of the
holding-
weight.
Are you holding it down or something? Yeah, you just hit it once and then you don't hold it down or anything.
Okay, thank you.
Got it?
Yeah.
Were you holding it down? Was that the issue?
Yeah, that might have been it. Maybe I was
Okay.
pressing it too hard by accident.
Yeah, these things are fairly delicate. I mean, they're not like the home scales, which could take a bit of a beating.
Should we note in our notes if it's not exactly 50 grams of water?
Definitely. Yeah,
Okay.
that's what taking notes is all about. Because one of the questions in your report is going to be, can you determine what the source of some of the errors are? And if you're gonna have errors, I'm gonna have errors, everybody has errors. And if you take really good notes during your experiment, you'll be able to refer back to it. Oh, right, I did that. Oops. Oh, right, I did that. Or, Dylan, I threw my cup across the room. So, stuff like that.
Okay.
All right, I'm gonna work on the calculations. Be right back. So I have my data for the first two, 0, 10%. So now I want to open up a plotting. All right. So I'm going to go to Google. Can everyone see my screen? Is that what I'm sharing? Can you see it?
Yeah.
Okay, cool. Google Sheets, our old friend Google Sheets. Start a new sheet. All right, so I have water. And I've got 10% sucrose. And I've got 5, so volume mils. And then up here, I've got grams, mass. All right, so we did 5, 10, 15, 20, and 25 mils. And so for water, oh, I need to subtract. My calculator. I forgot to subtract the mass of the cylinder. Oops. So 5.20. $10.31. $15.43. Oh, damn it. 15.43.
Professor, I have a question.
See,
So after we measure the sucrose, do we put it back in the cup?
I don't understand the question. Could you repeat that? Hello?
So like, you know, the water in the cylinder that we measure to get the sucrose, like, do we pour it back into the cup?
Oh, no, you can just dump it.
Oh, okay, thank you.
Yeah, you can just dump that. That's fine. I mean, you can pour it back if you want, but you know, generally it's something we don't want to do. We want to avoid contamination if at all possible. So generally, if we've been using, like for instance, if you're in a lab and you take some, if you're weighing out some like sodium chloride or something, and so you have a big bottle of sodium chloride, and
Thank you.
you don't ever pour it back into the container. If you have excess, you throw it away because we don't want to contaminate things. So it's a good habit to get into.
That's what they do for nursing too. If
Yeah.
you poured excess amount of the liquid, you know,
Throw
for
it away.
medication, yeah,
Yeah.
they throw it away.
Mhm. No, it's always the, you know, better part of discretion to do that. It avoids a lot of errors. Especially since, you know, if you've taken something out of the container, it may have come into contact with something else. It may be what's called hygroscopic, which means water starts to stick to it, which changes it. So yeah, basically once it's come out of the container, it doesn't go back in. Same thing goes for liquids too. If you're like measuring out, you know, ethanol or alcohol or or some organic solvent. If you don't use the rest of it, it does not go back. It just gets dumped into waste. $25, $33. All right. So there's my masses of the water, and they look pretty good. Sort of what you would expect. Okay. So here I've got my volumes here and my masses here. So now I want to plot them. So I select what I want to plot. And I go to Insert. I want a chart. I want a scatter chart. There it is. And it's given it to me. And see already, since it's 0% and 10%, my lines are going to be pretty close to each other. And you can see that there. So I want this, I want to have this be at 0. So I'm going to change the horizontal axis so I can see 0. There we go. All right. So now we want to have a trend line, if you remember. See if I can remember how to do that. We just click on it, right? Yeah. Come down here to trend line. I want a linear one. I want to show the R squared. Oh, wow, exactly 1. Come on. I mean, who are we dealing with here? And then I want to label the equation. Okay. Then I want to do the same thing for the next one. So I want a trend line. I want to see the R squared. Again, R squared is 1. I mean, you're dealing with a genius here, clearly. And then my equation. All right. So, but if you're, you can see that the y-intercepts are really close to 0. I mean, really, really close. But they're not exactly 0. So here is the line. This is the line for the water. And then this is the line for 10%. So you can see that the y-intercept is, especially for the 10%, is almost 0. It's really, really, really close. For the water, it's a little bit off. So remember, we want to force the y-intercept to go through 0. If you remember what we had to do to do that, it was equals, see if I can remember how this goes. Oh, right. LINEST. Best fit linear bracket, and then show it where the Y data is, and then comma, and then where the X data is, comma, false. And hit enter. You see the changes a little bit. So now the slope of my water is 0.120, meaning that the density of my water is 1.02 grams per mil. That is you can see my density would have been even closer if I hadn't put it through 0, because the original slope was 1.01 grams per mil. But that's pretty close. If you consider that's a 2% error, right? We should get 1. So if you get 1.02, that's pretty good. So we should be able to get the density of water pretty close. So let's do the same thing for the other data. So equals LINEST. There's my 10% Y data, comma, there's my X data, comma, false. So now that hasn't changed the slope at all. So the slope, this is my 10% sucrose. So you guys are going to do this for all of them, which is kind of why I maybe suggest just making the solutions tonight and doing the rest of it tomorrow, because it takes a while just to make the solutions. So according to this, the slope of my 10% sucrose solution is 1.061 over here. Oops. Right here. So 10% sucrose has a higher density, which it should, of 1.06 grams per mil. And so this should just keep increasing as you add more and more sucrose. I think it might even go up to like 1.5 grams per mil at the end, or maybe even more than that. It gets pretty viscous. So then once you've calculated the densities of your solid objects, like for instance, my polyethylene cylinder had a density of 1.09 grams per mil. So it probably will sink in 10% sucrose, but I'm betting it'll float on 20% because that density is really close to this one. So do you have any questions about how to handle the data? Would you like me to go through this one more time?
Yeah.
Okay, no problem. All right, let's.
Wait. So basically what you're doing is just comparing the mass of H2O to the mass of the percentage of sucrose, right?
Exactly.
For your solution. And then after that, you'd graph that. And then after that, you'd do
You get the density.
estimate.
You get the density from the slope of the line. Because remember, the slope of the line, since this is going to be mass, and this is going to be volume, and the slope of the line is y over x, then the slope of the line is going to be mass over volume. And what is that? That's density. So as long as you have the right units, you'll get density. So as long as your units are grams and mils, your density will be in grams over mils, which is what you want your density to be in. Because remember, so those of you who work in nursing or anything, I assume you still have syringes with like CC on them, right? Like 10
Usually
CC?
yeah, I mean,
cc's?
ml, cc, they're essentially the same.
Yeah, they're exactly the same. CC stands for cubic centimeters. So CC is equal to 1 ml. It's the exact same thing. So I think CCs is like an older, I think that's an older school way of showing volume. I think everyone uses mils now, but it's exactly the same. So let's go through how to do this one more time. All right, so I put my,
Sorry to
oh, go
interrupt.
ahead, no
So
problem.
for my sugars, you know, they don't have to be exactly like 5.5, 12.5, like because I got one like 5.51.
Oh my God, get out of my class, 5.51.
You know, so as
Just-
long as I
just-
at least
Just get out. I can't even bear to look at you.
as long as I report, you know, that there was a little bit of the discrepancy, then it should be
5.51,
fine.
I mean, yeah, I mean, you did, that's perfect. I mean, that's as good as it gets.
Okay.
Yeah, if you, that's like, you know, you have one more grain of sugar than you should. That's ridiculous. That's really accurate.
Okay, I'm just making sure because I'm trying to make it as accurate as the numbers, but it's pretty hard with, you know.
I'm not gonna lie, I've spent so long trying to get it to exactly 5.50, and now that I just hear this, I'm so sad.
Oh, if you get 5.49, yeah, go. Because because it doesn't say 5.50, does it? It says 5.5.
Oh,
There's only two significant digits, right?
oh yeah, that's true.
Yeah, so basically anything between 5.46 and 5.54, you're good.
What does
Yeah.
this lab do?
So don't spend half an hour trying to get
It's
5.50.
due next week. This lab is due next week, right?
Yes.
Oh, I thought it was due yet. Oh my gosh, I thought it was due tomorrow. I was like,
No, God,
No.
Oh
no.
no, that would make him really evil.
No, last week's is due today.
oh, okay. That
Yeah,
makes sense.
not this week's, my God. All right. So here are my volumes that I measured. So for each solution, you're going to measure these same five volumes, 5, 10, 15, 20, and 25 mils. So then I'm going to have 0% sucrose, 10, 20, 30, 40, 50, 60. Just have them all right there. And then I'm going to measure the mass of my 5, 10, 15, 20, and 25, and just have them here. So then I just select as many points as I want. If I just have 0% and 10% right now. So that's all I can select. Make sure that the x-axis is first. So make sure that your x-axis is the very first column, and any additional columns after that will be considered y by the computer. So then we go over here to insert. What do I want to insert? I want to insert a chart. And you can see already that it pretty much figured out that what I want is a scatter plot. If it isn't a scatter plot, you would select that right up here, chart type. You can change it to something else. But scatter is what we want because we want to be able to see each individual point. I can also blow this up to make it a little bit easier to separate these points. As you can see, they're super, super close together. The other thing I can do is make sure that my volume goes to 0. So I just double click on that. Go to my horizontal axis and say I want, oh, wait a minute, horizontal axis, here we go. I want the horizontal axis to start at 0. So my minimum value will be 0. So you see it changes it from 5 to 0. That gives me a better idea of what my y-intercept is going to be. So now I want to figure out what the relationship is between the volume down here and the mass over here. I could also put a label on, I should have a label on my y-axis, because you're gonna copy and paste this into your report. So you should have a nice title up here, something like calculating density of sucrose solutions. Something like that. So now to get the fit, the whole point of doing this was to get a line, because I want the slope of the line to tell me what the density is, because the slope of this line is going to be mass, which is y, over volume, which is x. And the slope of the line is y divided by x. So as long as my mass is in grams, which it is, and my volume is in milliliters, which it is, the slope of the line will be equal to the density in grams per mil. But I need the slope of that line in order to figure it out. So in order to get the slope of the line, I just double click on one of the data points. So if I double click on this blue point, series will pop up to my right, and I scroll down and I say, I want a trend line. What kind of trend line? I want a linear one. I also want to see the R squared, and I want to label the equation. I want to see what the equation is. So here, this tells you what the equation is. So the blue is for just water. So I think I can label that. Yeah, I can label that somewhere. Oh, maybe here. Anyway, you want to keep straight which is which. So that is the slope for my just water. So to get the slope for my 10% sucrose, I double click on one of the red points, which is my 10%. So here's my red points. I want a trend line for that. I also want it to be linear, and I want to see the R squared. So you can see you're going to get some really good data. If you take your time measuring the volumes carefully, you're going to get really good data. You can see that the R squareds for these are 1, meaning that every point is exactly on the line. I'm also a professional, so that's going to happen. So those are the, oh, I also want to see label, I want to see the equation. Right, so this one, the slope of this line is the density of the water in grams per mil. The slope of this line is the density in grams per mil of the 10% sucrose solution. But the instructions in the for the experiment want you to put the y-intercept at 0. And you can see it's close to 0 for both of these, but it's not quite. The y-intercept for my water is a little bit above 0, and the y-intercept for the 10% is almost exactly 0. It's really, really close. But the instructions say put it through 0. So how do we do that? So we come over here and we write down equals LINEST for best fit linear trend. Brackets, and then you show which Y data you want. So the Y data I'm going to do first is for water. So I just select the Y data for the water, basically the masses. Then I put a comma, and then I select the X data for the mass, for the water. And this will always be the same for the 10%, the 20%, for all of them. And then this is the key, comma, false. that says to the computer, I don't want the y-intercept where you think it is. Put it into 0. I think that y-intercept is false. I want 0 as the y-intercept. Then close the bracket and hit enter. So now what comes out is the new slope and the new y-intercept. So the new slope, instead of 1.01, is now 1.02. And the y-intercept, instead of being 0.224, is now 0. So that is my water, and that tells me that the density of my water, I calculated, is 1.02 grams per mil. And this is the equation I would put in on the chart. Y is equal to 1.020 x. Remember, there's no plus b, so that is the equation, and this is the slope. And then we just do exactly the same thing for my 10% data. So I go equals LINEST brackets. Where's the y data for my 10%? There it be. Comma. There's my x data, which would be the same for everybody. Comma, false. Hit enter. So this is the new slope for the 10% sucrose. And you can see that the slope for the 10% sucrose hasn't changed. It's 1.06 here, and it's 1.06 here, which makes sense because the y-intercept originally was so close to 0, it was practically 0. So by moving it to 0, we haven't changed the slope at all. So my 10% sucrose equation is y is equal to 1.06 x. And the density is 1.06 grams per mil. And so you basically just keep doing the same thing for your 20, 30, 40, 50, 60. The calculations will be super fast, especially if you do them all at the same time. Super, super quick. And then it's just a matter, you have one more plot you have two more plots to do. One is figuring out the density of your beverage by doing exactly the same thing as we've done here. And then the last thing you will do is you will take all of your densities, so your 0, 10, 20, 30, 40, 50, 60, and your densities, and you will plot them. Percent sucrose on the X and density on the Y. So what this will give you is a relationship between the percent sucrose and the density. So as we see, the more sucrose in the solution, the higher the density. So what this does will help you figure out precisely what the percent sucrose in your beverage is. How? Because you're going to determine what the density of your beverage is. So once you know what the density is, let's say the density is, so this is 0, 10, 20, 30, 40, 50, and the density goes from 1, let's say, up to 2, 1.5. Let's say your density is like 1.4 grams per mil. So this is the density of your beverage. Then you just come over here, find where 1.4 is, 1.4. Straight line to the line and then come down. And that tells you that the percent sucrose is around 35%. So is that clear for everybody? I can hang for a little while longer to answer questions. I just want everyone to be clear on what it is they're doing. All right, so where is everybody?
So
Where's
basically,
everybody?
it's just mass volume, right? And then, or like, like using those two values to get density, correct?
That's all we're doing here.
Yeah, yeah. And then after that, when you find all of that, for like, let's just say, for example, like 10% sucrose, and you would put it onto you'd graph it, right? And then make a chart. And then,
Well, the last one, we want to see what the relationship is between
yeah.
the amount of sucrose and the density. So
Mhm.
that won't give us, that slope of that line won't give us density. That just gives us.
So your data would give you the relationship, though, right? Just by looking at it, correct?
Yeah, exactly. Just by looking at it, you could probably estimate
Mhm.
approximately
Mhm.
what the percent sucrose is, but if you plot it, you'll be able to get it much more accurately.
Oh yeah, yeah.
And you should be able to calculate what it is just by looking at the label. It should tell you exactly how much sucrose is in there. Unless of course, it's, high fructose corn syrup, which most American beverages are sweetened with. So that's not quite the same thing. Fructose is fruit sugar, which is extremely similar to sucrose, but it's not exactly the same. So is everyone clear on how to proceed? Don't make it too late at night. Probably just finish making your solutions and then have a nap. Right, you got a whole week. But don't wait. But if you've made 3 solutions tonight, don't dump them out and start over. I mean, hang on to them. Do the other 3 tomorrow. Karina, how you doing? Yeah. You look crushed. All right, that's good. So anybody else have any questions on how to proceed? Does it seem so? Find a beverage if you haven't got one in the house tonight that you want to use. Just go get one tomorrow. Like apple juice is a good one. I think someone mentioned coconut water. I don't know how much sucrose coconut water has in it, but it's not supposed to have any, right? I think it just has like natural fructose in it. So, but that's fine. You're gonna want something that has between 10 and like more than 10%. And like something like Coca-Cola has a ton. So
Is it okay that the 50% water doesn't look clear anymore after I put the sugar in?
oh, definitely. The 50%. Yeah, once you get over 50% or 40% sucrose, it starts looking a little yellow, right?
It looks more whitish, like, sugar color.
Yeah.
Okay.
Because it probably hasn't dissolved yet. But when it all goes into solution, it'll actually start to look a little yellow. And that's just because of the light scattering. We'll make it look a little dirty. Like really dense solutions tend to scatter the light a little bit more. So even if it's a completely pure crystalline white solution, it'll look a little dark because of that.
Yeah, it looks like this.
Mm-hmm.
Okay.
That's not all in solution yet.
So should I just stir it more, or?
I would heat it for like maybe 10 seconds, 5 or 10 seconds in the microwave, and then stir it.
Okay.
Yeah, just real briefly.
Oh,
You don't want
look
to
at
do it
this.
any longer than that because that'll melt.